The ocean is 4 billion years old, and for most of that time, it holds nothing that would frighten you. Just water, warm and mineral heavy, moving over a young seafloor still cooling from the planet's birth. There is no sound here, because there is nothing yet with ears to notice its absence. This changes, slowly, and then less slowly, and then in ways that eventually produce something the modern mind calls a monster. The ocean itself never used that word, and never needed one. It only needed conditions, time, and pressure of a different kind. The pressure of survival, repeated across billions of generations, refining shape after shape until some of those shapes became difficult to look at directly. Even now, even as stone. Picture the earliest version of this water. The sky above it is a strange color, thick with gases no land animal will ever breathe. Meteors still fall often enough to matter, some large enough to vaporize entire stretches of ocean on impact before the water slowly refills the crater they leave behind. The moon sits closer than it does today, dragging the tides higher and faster across a coastline that has no name and no witness. Volcanic islands rise and erode within time frames that would seem impossibly fast if any observer existed to watch them, adding minerals and gases to an ocean still finding its chemical balance. There is no fixed shoreline, in any sense a modern mind would recognize. No permanence to any single feature of this early world, only slow, continuous change happening at a pace too vast to observe directly, even if something had been alive to try. Beneath the surface, along cracks in the seafloor where mineral-rich water vents into darkness, something is happening that will not stop for the next 4 billion years. A molecule begins copying itself. It is not alive in any way you would recognize, but it is the first thread of a story that ends, eventually, in Jaws. Consider how long this quiet stretch actually lasts. If the 4 billion years were compressed into a single day, the first predator would not appear until well into the evening, somewhere close to 9 o'clock at night. With everything that follows every jaw, every armored giant, every reptile and whale and shark described in the hours ahead crowded into the final few hours before midnight. Most of this ocean's history, by far, belongs to that long, uneventful afternoon and evening, a stretch of time so vast and so still that it can be difficult, even now, to hold its true scale in mind. For a long time, longer than is easy to hold in the mind, nothing hunts anything. Life exists as single cells, drifting or clinging to rock, absorbing what the water offers without needing to chase it. There is no urgency in this ocean, because urgency has not been invented yet. It will take more than 3 billion years before anything develops the shape, the nervous system, or the appetite required to become a predator in the way we now understand the word. Then, in a span of geological time so short it looks almost like an accident that changes everywhere at once, the ocean, which had been patient for so long, suddenly fills with animals built to eat one another, and within a few tens of millions of years, an arms race begins that has not, in truth, ever really stopped. Tonight, we follow that arms race from its first quiet skirmishes to its most extreme results. Animals so specialized for killing that later generations, encountering only their fossils, would describe them using the language of nightmare. We move through the Cambrian seas where the first true predators appear, through Ordovician waters patrolled by shelled giants and armored scorpions, into a Devonian ocean ruled by fish with blades instead of teeth, and onward through the long return of reptiles to the water, the age of sea dragons that followed, and the rise of the largest predatory shark to ever hunt. We end where the story is not yet finished in the deep ocean of the present, where more remains unmapped than mapped, and where the pattern that built every creature is, in all likelihood, still quietly at work. This is not a story about malice. The ocean does not choose fear, and nothing in it has ever hunted out of cruelty, but it does choose survival, relentlessly, and survival has produced some of the most unsettling animals this planet has ever assembled. We begin almost 4 billion years ago, in water so still and so empty that nothing in it could yet imagine what it was about to become. Before we go further, it helps to set the terms of this story honestly. The word nightmare belongs to us, not to the ocean. Every animal in the hours ahead was simply solving a problem: how to eat, how to avoid being eaten, how to survive one more season in water that offered no mercy and asked for none. What looks like horror from the distance of hundreds of millions of years was, at the time, only strategy. The fossil record that lets us tell this story is not complete, and it never will be. Soft tissue rarely survives. Entire lineages exist for us only as fragments: a jaw here, a claw there, an impression in fine-grained shale that happened to form under exactly the right conditions to preserve an animal that would otherwise have vanished without a trace. Where the record goes quiet, we will say so plainly. Where scientists disagree about size, behavior, or appearance, we will describe the disagreement rather than pretend it does not exist. It helps, too, to remember how uneven this record is across different periods of time. Some chapters of the ocean's history are known from thousands of well-preserved specimens, recovered from dozens of sites around the world, allowing a fairly confident reconstruction of how a given animal looked, moved, and hunted. Others survive only as a small handful of fragments, sometimes just one, found in a single location and never matched anywhere else on the planet. This unevenness means our confidence in the details of this story is not the same from one chapter to the next, and honest science requires acknowledging exactly where that confidence is strong and where it is considerably more limited. What follows is organized the way the ocean itself unfolded, not by drama, but by time. Each chapter moves the story forward by tens or hundreds of millions of years, tracing how predation was invented, refined, interrupted by extinction, and reinvented again, each time producing animals suited to whatever ocean happened to exist at that particular moment in Earth's long history. Some of these animals will be familiar, many will not. All of them were, in their own time, simply trying to survive until morning, a concept that, in the deep past, did not yet include a sun to mark it. We start with the first true hunters, in a Cambrian sea barely 500 million years old, where an entire new way of being alive is about to begin. 541 million years ago, the ocean looks almost peaceful. The sea floor is soft and undisturbed, layered with mats of bacteria that have covered the bottom of shallow seas for tens of millions of years without much competition. Strange, flattened creatures drift or sit atop these mats, absorbing nutrients directly through soft bodies that have no mouths, no eyes, and no apparent need for either. This world is called the Ediacaran, and it is, by most measures, gentle. It will not stay that way. Much of what is known about this period comes from a small number of exceptional fossil deposits, places where conditions happened to preserve soft tissue that would normally decay long before it could ever turn to stone. The Burgess Shale, in what is now Western Canada, and the Chengjiang deposits in southern China, both capture Cambrian animals in extraordinary detail, including delicate limbs, gut contents, and even traces of muscle tissue that offer a far more complete picture of Cambrian life than the hard shells and armor plates that make up most of the fossil record from other periods. Without these rare sites, much of what this chapter describes would remain entirely unknown, reduced to fragments of shell with no way of reconstructing the living animal that once carried them. Something shifts in the chemistry of the ocean around this time. Oxygen levels climb. Simple genetic tools, already present in ancient organisms, begin to be used in new combinations, producing body plans more complex than anything that came before. Within a window of perhaps 20 million years, a blink, by the standards of deep time, animals with hard parts, segmented bodies, jointed limbs, and functioning eyes appear across the world's oceans almost simultaneously. This is the event now known as the Cambrian explosion, and it is the true beginning of the story this documentary is telling. Among the first animals to take advantage of this new complexity is a creature that would come to dominate Cambrian seas for millions of years. Anomalocaris. Its name means strange shrimp, though it resembles neither grows to nearly a meter in length, making it a giant by the standards of its time. When most animals could fit comfortably in the palm of a human hand, two long spined appendages extend from its head, curling forward to grasp prey. A circular mouth lined with plates sits beneath its body, opening and closing to crush whatever those appendages deliver to it. The speed of this transformation has puzzled researchers since the Cambrian explosion was first recognized as a distinct event, and several explanations have been proposed rather than a single agreed-upon cause. Rising oxygen levels, discussed briefly above, appear to be part of the story, since more oxygen supports larger, more energetically demanding bodies and the muscle tissue required for active hunting. The evolution of vision is another likely contributor, since the ability to see prey, predators, and potential mates changes the pace and nature of natural selection considerably, compared to a world where animals can only sense their surroundings through touch or chemical cues. Genetic flexibility, particularly in the regulatory genes that control how an embryo develops its body plan, may have reached a tipping point around this time as well, allowing small mutations to produce large, functional changes in body structure, rather than simply minor variations on an existing theme. Most likely, no single explanation accounts for the entire event. It appears instead to be the product of several favorable conditions, converging within a relatively narrow window of geological time. This is the first apex predator the ocean has ever produced, and its arrival changes everything downstream of it. Trilobites, small, armored arthropods that will go on to survive for nearly 300 million years, develop increasingly elaborate shells and spines during this period, and many paleontologists believe this defensive architecture is a direct response to Anomalocaris and animals like it. Some trilobite fossils even preserve what appear to be healed injuries, bite-shaped gouges taken out of their armor and repaired as the animal continued living. Predation, in other words, is no longer a rare event. It is now a constant pressure shaping the bodies of everything in the water. Anomalocaris is not alone in this new business of hunting. Smaller predators work the same waters using different methods entirely. Sydnea, a flattened arthropod roughly 10 centimeters long, scavenges and hunts along the seafloor, its gut contents preserved well enough in some fossils to show fragments of trilobite shell and other hard-bodied prey, direct evidence of exactly what it was eating in its final hours. Priapulid worms, unassuming in appearance, turn out on closer study to have been active burrowing predators, pulling their entire bodies backward into the sediment to ambush anything that ventured too close to the opening they left behind. Predation, once it arrives, does not take a single shape. It arrives everywhere at once, in bodies large and small, fast and patient, each testing a different method against the same basic problem of finding the next meal before becoming one. Elsewhere in these Cambrian seas, evolution is experimenting in directions that will not always succeed. Hallucigenia moves along the seafloor on rows of spiked legs, so strange in structure that when first described, scientists mounted its fossil upside down, mistaking its spines for legs and its legs for spines. Opabenia carries 5 eyes on stalks and a single flexible proboscis tipped with a claw, an arrangement so unusual that no other animal, before or since, has repeated it. Most of these experiments end in dead ends. A small number do not, and one of the survivors matters more than any other creature in this chapter. Pikaia is unremarkable to look at a slender, worm-like animal a few centimeters long, swimming with side-to-side undulations through open Cambrian water. It has no armor, no claws, and no obvious weapons. What it has instead is a notochord, a flexible rod of supportive tissue running the length of its body. This is the earliest known structure of its kind, and it places Pikaia, or animals, very much like it, at the root of the lineage that will eventually include every fish, every marine reptile, every whale, and every predator described later in this account. The nightmare shapes of the deep future begin, quietly and without any indication of what is to come, in an animal built for nothing more dramatic than staying alive in open water. The Cambrian seas that hold all of this life are shallow and warm, spreading across continental shelves in conditions very different from anything in the modern ocean. Oxygen is less abundant than it will later become, which limits how large any single animal can grow. This is part of why Anomalocaris, at roughly a meter long, counts as gigantic in this period, even though later chapters in this account will describe predators dozens of times its size. Scale, in the story of the ocean, is not fixed. It expands and contracts according to the chemistry of the water and the atmosphere above it, a pattern that will repeat again and again across the next 500 million years. What makes the Cambrian explosion significant is not simply that new animals appear. It is that an entirely new relationship between animals appears alongside them, a feedback loop in which being eaten drives the evolution of defenses, and those defenses drive the evolution of better methods of attack, each side of the relationship pushing the other further with every passing generation. This loop, once started, does not stop. It becomes the engine that builds every predator described in the chapters ahead, refining teeth, jaws, size, and strategy across hundreds of millions of years of ocean history. Eyesight itself deserves particular attention here, because its arrival changes the rules of this ocean as much as any single predator does. Before the Cambrian, no animal appears to have possessed anything resembling true image-forming vision. Once eyes appear, first as simple light-sensing patches and quickly afterward as compound structures capable of detecting shape and movement, the entire relationship between predator and prey shifts. An animal that can see an approaching threat can also flee from it, hide from it, or freeze against a matching background rather than waiting to be touched or tasted before reacting. Trilobites, among the first animals to develop sophisticated compound eyes, owe much of their long-term survival, nearly 300 million years, longer than almost any other animal lineage described in this account, to exactly this innovation. Wiwaxia, a small, scaled animal covered in overlapping plates and long defensive spines running along its back, represents another kind of answer to the same pressure. Rather than seeing danger coming, Wiwaxia simply makes itself difficult to swallow. Its armor arranged less like a shield and more like a set of raised blades pointed outward in every direction. Fossils of similar armored, spined animals recur throughout Cambrian deposits worldwide, suggesting that this particular solution, passive defense through discomfort rather than active flight, proved successful enough to be tried again and again by unrelated lineages facing the same predators. By the close of the Cambrian period, roughly 485 million years ago, this engine has already produced predators that would have been unimaginable at the period's beginning. It is easy, from this distance, to imagine the Cambrian seas as some primitive rehearsal for the ocean's later, more dramatic chapters. This is not quite accurate. The animals living through this period were not incomplete versions of anything. They were fully formed, fully functioning creatures, well suited to the water they lived in, facing real pressures and solving them in real time, with no sense that they were part of an early act in a much longer play. The Cambrian Ocean deserves to be understood on its own terms, as a complete and often strange world, rather than merely as a prologue to the more familiar-looking predators still tens of millions of years away. Anomalocaris itself does not survive to see the next chapter of the story. Its lineage fades as new competitors arrive, better suited to a changing ocean. But the pattern it represents, the first true blueprint of ocean predation, does not fade with it. It simply moves forward, into deeper water, into stranger shapes, and into scales of size the Cambrian world had no way of producing yet. This feedback loop between predator and prey, once established, rarely runs in only one direction for long. A defensive innovation that succeeds against existing predators creates selective pressure favoring any predator capable of overcoming it, which in turn creates pressure favoring the next defensive innovation, and so on. Indefinitely, for as long as both lineages persist. It is a pattern that will recur, in different forms and among entirely different animals, throughout every remaining chapter of this account, from the armored fish of the Devonian to the heavily toothed reptiles of the Cretaceous, to the whales and sharks of the more recent past. The Cambrian seas are simply the place where this pattern begins, quietly, without any indication of how far it will eventually be carried. There is no single moment that marks the end of this chapter of the ocean's story. No clear dividing line between the Cambrian world and whatever follows it. Change of this kind arrives the way most change in deep time arrives gradually, through the slow accumulation of small advantages, until one day, the animals swimming through a particular stretch of water bear only a passing resemblance to the ones that swam there 10 million years before. The Cambrian seas do not vanish so much as they are quietly replaced, generation by generation, by descendants better equipped for whatever comes next. The Ordovician period is beginning, and the ocean is about to grow considerably more dangerous. The map of the world during the Ordovician bears almost no resemblance to the one familiar today. Most of the planet's landmasses are gathered into a single large continent positioned near the South Pole, while the rest of the globe is covered by a single vast ocean, uninterrupted by the familiar continents that will not exist in anything like their current arrangement for hundreds of millions of years to come. This arrangement of land and water shapes ocean currents, temperature bands, and the distribution of life in ways quite different from the modern ocean, producing broad, warm, shallow seas across much of the tropical and temperate latitudes, ideal conditions for the reef ecosystems, and diverse invertebrate life that come to define this period. The Ordovician Ocean, beginning around 485 million years ago, is warmer than today's, and considerably more crowded. Coral reefs appear for the first time in this period, built not by the corals familiar to modern divers, but by early relatives working alongside sponges and algae to form the first true reef structures in Earth's history. These reefs become cities of shelter and ambush, crowded with life in a way the more open Cambrian seas rarely were. Where there is shelter, there is also the opportunity to hide, to wait, and to strike. And the Ordovician produces predators built for exactly that purpose. Chief among them are the nautiloids, shelled relatives of today's squid and octopus, though almost nothing about their scale would suggest a family relationship. Camarasaurus, one of the largest, carries a long, cone-shaped shell that some estimates place at close to 6 meters in length, making it among the largest animals in the entire ocean at the time. It drifts or swims slowly through open water, tentacles extended from the wide end of its shell, waiting for smaller animals to come within reach. There is no fast, darting attack here. The nautiloid's advantage is patience combined with raw size, an approach to predation that trades speed for the simple fact that almost nothing else in the ocean is large enough to fight back. Camarasaurus is far from the only shelled predator in these waters, only the largest and most striking example of a much broader group. Smaller nautiloids, curved rather than straight-shelled, patrol reef margins and open water in a range of sizes, each species tuned to a slightly different combination of prey and habitat. Some appear built for hunting soft-bodied animals in open water, their shells light and their tentacles long. Others, more heavily built, seem suited to a slower, bottom-hugging life among the reef structures, ambushing trilobites and other armored prey that ventured too close to a crevice already occupied. On the seafloor and in shallower water, a different kind of predator is developing, one with no shell at all, but with an entirely different form of armor. The Eurypterids, often called sea scorpions, though they are more closely related to modern horseshoe crabs than to true scorpions, grow claws, plated exoskeletons, and in some species, paddle-like limbs suited to swimming rather than crawling. Jacalopterus, appearing slightly later in this same broad window of ocean history, will eventually reach lengths of roughly 2.5 meters, making it the largest arthropod known to have ever lived, its claws alone stretching nearly 0.5 meter from base to tip. These claws are not decorative. Fossilized remains show clear evidence of a grasping, crushing function, well suited to holding struggling prey against the current while the Eurypterid's mouthparts do their work. It is difficult to reconstruct exactly how these animals hunted, since no soft tissue survives to describe their behavior directly. But the architecture of the claw, long, serrated, hinged for a fast closing motion, suggests an ambush predator, one that relied on surprise and grip rather than pursuit. Some Eurypterid species appear to have been adapted more for swimming in open water, with broad, flattened paddle limbs suited to active pursuit, while others show more robust, walking adapted limbs, suggesting a life spent primarily along the seafloor, ambushing prey that wandered too close. This range of body forms within a single broad group mirrors a pattern already familiar from the nautiloids described earlier in this chapter, and one that will recur throughout this account. A successful basic body plan, once established, tends to diversify into multiple specialized variants, each suited to a slightly different way of finding the next meal. Meanwhile, in the same waters, a quieter revolution is underway. The descendants of Pikaia and its relatives have continued diversifying, and the first true vertebrates with bone rather than cartilage begin to appear during this period. Early jawless fish, covered in bony armor plates rather than scales, move slowly along the seafloor, filtering small particles of food rather than hunting actively. They are not yet predators in any meaningful sense. They lack jaws entirely, relying instead on simple, sucking mouths, unsuited to biting or tearing. But the bone that reinforces their bodies and the basic vertebrate architecture underlying them will eventually give rise to every fish, every shark, and every marine reptile described in the chapters that follow. The armor came first. The jaws are still to come. Even the reef-dwelling animals that could not fight back directly benefit, in aggregate, from this new architecture of hiding places. A reef with more nooks and overhangs supports more prey animals overall than an open, featureless seafloor, even though any individual animal sheltering there still faces real danger from predators specifically adapted to hunting within tight spaces. Abundance and danger, in other words, rise together in this new reef environment, rather than one canceling out the other. Trilobites, already carrying defensive spines and rolled-up escape postures inherited from their Cambrian ancestors, continue adapting throughout the Ordovician in direct response to these new hunters. Some species develop long, forward-pointing spines along their heads, likely intended to make them awkward to swallow. Others grow eyes on raised stalks, granting a wider field of view suited to spotting an approaching nautiloid or Eurypterid before it closes the distance. None of these adaptations make trilobites safe. They simply make them slightly harder to kill, which, across millions of years and countless generations, is often the only advantage evolution requires. The reefs themselves add a new dimension to this arms race that the more open Cambrian seas never had. A flat seafloor offers nowhere to hide, which favors predators built for open pursuit or overwhelming size. A reef, by contrast, offers crevices, overhangs, and shadow, favoring ambush over pursuit. Fossil evidence from Ordovician reef deposits shows a far greater diversity of body shapes than earlier periods, flattened animals suited to squeezing into narrow gaps, heavily armored animals suited to withstanding an attack they cannot avoid, and fast-swimming animals suited to abandoning the reef entirely rather than risk being cornered within it. The reef does not just house more life, it reshapes the rules by which that life survives. Above the reefs, in open water, jawless fish continue growing more numerous, though they remain a minor presence compared to the arthropods and cephalopods that dominate this ocean. Their armor plating, made of true bone rather than the chitin-covering trilobites and eurypterids, represents a different evolutionary solution to the same basic problem: how to survive in water full of animals equipped to kill you. Bone has properties that chitin does not. It can be repaired through living tissue rather than replaced through molting, and it can be reinforced in specific locations without adding weight everywhere at once. This flexibility will matter enormously in the chapters ahead, though nothing in the Ordovician Ocean yet suggests how far that particular building material is capable of going. Fossils of the largest eurypterids are exceptionally rare, and most of what is known about animals like Dunkelosteus comes from isolated fragments of the exoskeleton, particularly the claws, rather than complete specimens. Reconstructing total body length from a single claw fragment requires comparison with more completely preserved smaller relatives, then scaling those proportions upward, a method that carries a degree of uncertainty similar to the tooth-based size estimates used elsewhere in this account for extinct sharks. Even accounting for this uncertainty, the largest known claw fragments leave little doubt that Dunkelosteus and its close relatives were substantially larger than any other arthropod known to have existed before or since, a record that still stands today. The Ordovician Ocean, for all its predators, is not a stable place to live. Roughly 445 million years ago, conditions begin changing in ways that will end this chapter of ocean history abruptly. Much of the planet's water becomes locked into massive glaciers as a period of intense global cooling begins, and sea levels drop sharply as a result. Habitats that had existed for tens of millions of years, the shallow continental shelves where reefs, nautiloids, and eurypterids had built their world, shrink or disappear entirely. What follows is now recognized as the late Ordovician mass extinction, one of the 5 largest extinction events in the planet's history, removing an estimated 85% of marine species within a relatively short span of geological time. Much of what is known about the glaciation behind this extinction comes from chemical signatures preserved in ancient rock layers, particularly variations in oxygen isotopes that shift in predictable ways as global ice volume changes. These signatures, recovered from rock formations on multiple continents, allow researchers to reconstruct the pace and severity of the cooling with a level of confidence that would be impossible from fossil evidence of marine life alone. 2 closely spaced pulses of extinction appear in the record, separated by a short interval rather than a single continuous event, suggesting a complex unfolding crisis rather than one simple cause acting in isolation. The exact mechanisms of this extinction remain a subject of ongoing research. Cooling and falling sea levels appear to be central causes, but some researchers have also proposed that a burst of radiation from a nearby stellar event may have damaged the ozone layer during roughly the same period, though this remains one interpretation among several rather than settled fact. What is clear from the fossil record is the outcome: reef ecosystems collapse, and many of the largest nautiloids and eurypterids vanish from the record entirely, their lineages either extinguished outright or reduced to a fraction of their former diversity. Recovery from an extinction of this scale is never immediate. For several million years following the initial glaciation and its associated die-off, the fossil record shows what paleontologists sometimes describe as a depleted ocean, fewer species, simpler ecosystems, and a noticeable absence of the largest predators that had defined the period before. Reef building all but stops for a time, and the elaborate, densely populated shelf communities that had taken tens of millions of years to assemble do not simply reappear. They are rebuilt, slowly, by survivors and their descendants, working from a much smaller starting pool of body plans than existed before the crisis began. The ocean that emerges on the other side of this extinction is emptier, quieter, and in many ways starting over. But the underlying pattern established in the previous chapter has not disappeared. Predation as a survival strategy has proven itself too effective to abandon, and within a few million years, new animals begin filling the gaps left behind by the eurypterids and nautiloids that did not survive. Fish, still armored, still jawless, continue slowly refining the vertebrate body plan that arrived quietly in the Cambrian. Somewhere in that refinement, a hinge is about to appear in the front of a fish's skull. A small anatomical change that will do more to reshape the ocean's predators than almost any single development before or since. The age of the jaw is beginning. By the time the Devonian period begins, roughly 419 million years ago, the hinge that appeared quietly in the skulls of jawless fish has had tens of millions of years to develop into something far more capable. Jaws, once established, do not remain simple. They diversify rapidly, appearing in a wide range of shapes and sizes across an entire new group of animals, and within a relatively short span of time, fish move from a minor presence in the ocean to its dominant predators. This period will later be known, informally, as the Age of Fishes, and for good reason. The land bordering these Devonian seas is also changing rapidly during this same period, and the two transformations are not entirely separate from one another. The first true forests appeared during the Devonian, their roots reaching deeper into soil than any plant structure before them, altering the chemistry of rivers and coastlines, as rainwater carries nutrients and sediment into the ocean in quantities and patterns unlike anything in earlier chapters of this account. Some researchers propose that this new nutrient runoff may have contributed to local algal blooms and oxygen depletion in certain coastal waters, an early example of land-based change directly reshaping ocean conditions, a pattern that will recur, in various forms, throughout the rest of this planet's history. Oxygen levels during the Devonian climb higher than they had been in the preceding Ordovician and Silurian periods, a change linked in part to the rapid spread of early plants across the land, which increases the rate at which oxygen enters the atmosphere, and eventually, the ocean. Higher oxygen availability supports larger, more active bodies, removing one of the practical limits that had kept Cambrian and early Ordovician predators comparatively modest in size. This is not the only factor behind the scale reached by Devonian predators, but it forms part of the backdrop against which the placoderms and early sharks of this period were able to grow as large as they did. Among the fish that emerged during this period, one group in particular reshapes what a predator in the ocean is capable of becoming. The placoderms are armored from the head backward, their skulls and upper bodies covered in thick, interlocking plates of bone, while the rear portion of their bodies remains more flexible, built for propulsion rather than defense. Instead of teeth in the conventional sense, many placoderms carry sharpened, blade-like extensions of this same bony armor along the edges of their jaws, structures that function like teeth, wear like teeth, and in some species, sharpen themselves continually as the upper and lower blades grind against one another with each bite. The largest and most capable of these armored fish is dunkleosteus, and it deserves the bulk of this chapter's attention, because almost nothing in the ocean before it has combined size, armor, and bite force in quite the same way. Estimates of its total length vary considerably depending on the study, with some older reconstructions suggesting close to 9 meters and more recent, conservative analyses placing it closer to 4 meters, still an imposing size for this period of ocean history, even at the lower end of that range. What is not in dispute is the design of its head. A thick shield of bone covers the skull and the front third of the body, hinged at the neck in a way that allows the jaw to snap open and shut with unusual speed, creating a powerful suction effect that draws prey directly into the waiting blades. Reconstructing an animal like dunkleosteus is more difficult than it might first appear, since only the front, armored portion of its body tends to survive as fossil material, the rear of the animal apparently supported by cartilage that decays long before it can be preserved. This means that most of what is known about dunkleosteus comes from skull and armor fragments alone, leaving the overall body shape, swimming style, and even total size a matter of ongoing reconstruction and revision as new specimens are discovered and older estimates are reassessed using updated methods. This uncertainty is worth stating plainly, in keeping with the honest handling of incomplete evidence that runs through every chapter of this account. What is not in dispute, regardless of exactly how long the animal's soft-bodied rear section extended, is the design and function of its armored, blade-lined head. Biomechanical studies of dunkleosteus jaws have estimated bite forces at the tip of its blades, reaching several thousand pounds per square inch, among the strongest bite forces calculated for any fish, living or extinct. This is not simply a matter of raw muscle. The hinge mechanism in its skull functions almost like a mechanical lever, multiplying the force generated by its jaw muscles well beyond what the muscle tissue alone would produce. Fossil evidence includes partially digested remains of other placoderms, and even what appear to be examples of dunkleosteus attacking members of its own species, their armor plates showing bite marks that match the blade shape of another dunkleosteus exactly. This is worth sitting with for a moment. An animal capable of biting through the armor of another heavily armored predator, sometimes including members of its own kind, represents one of the more extreme results of the arms race that began in a much gentler form back in the Cambrian seas of the first chapter. The defensive plating that had protected earlier fish from claws and crushing mouths proved insufficient against a jaw specifically evolved to cut through exactly that kind of protection. Armor and blade had, once again, escalated together, each pushing the other toward more extreme solutions. The success of the placoderms as a group extends well beyond dunkleosteus itself. Smaller relatives occupy a wide range of ecological roles throughout Devonian seas, some feeding on shellfish with crushing plates rather than blades, others remaining bottom dwellers that rely on camouflage against the seafloor rather than active pursuit. This diversity matters because it shows that the placoderms were not a single, narrow experiment that happened to produce one giant. They were, for a time, one of the most successful and varied body plans the ocean had ever produced, filling roles that would later be occupied by an entirely different group of cartilaginous predators once the placoderms themselves were gone. Dunkleosteus does not hunt alone in this ocean. Early sharks, including genera such as colossal, patrol the same Devonian waters, though they take a very different approach to predation. Rather than armor, colossal relies on speed and a streamlined body shape that would look recognizably shark-like to a modern observer, despite being separated from any living shark species by hundreds of millions of years. Its teeth are already specialized for gripping slippery prey such as early fish and cephalopods, suggesting an active, pursuit-based hunting style rather than the ambush ferocity of an armored placoderm. Two very different solutions to the same problem exist side by side in this ocean, one built on armor and overwhelming force, the other on speed and precision. Shark teeth from this period, though smaller and less imposing than the armored blades of dunkleosteus, show a surprising range of specialization once examined closely. Some early shark species carry narrow, needle-like teeth suited to gripping soft-bodied prey such as early cephalopods, while others show broader, more robust teeth suggesting a diet that included harder-shelled prey. This diversity of tooth shape, appearing so early in shark evolutionary history, suggests that the basic template established during the Devonian proved flexible enough to be adapted repeatedly over the following hundreds of millions of years, a flexibility that later chapters of this account will show sharks continuing to exploit long after the placoderms themselves have vanished entirely. Beneath the surface drama of these predators, a quieter transformation is also underway, one that will matter enormously to the story of life on land, even though it belongs, for now, to the ocean and its shallow margins. Certain lobe-finned fish, distant relatives of the ray-finned fish that dominate most of the Devonian's open water, begin developing thicker, more muscular fins supported by bones that resemble, in miniature, the arm and leg bones of later land animals. Tiktaalik, one of the most famous examples, retains gills and scales suited to life in water, but also possesses a flexible neck and a skeletal structure in its fins, capable of supporting some weight, features more commonly associated with animals that walk than animals that swim. The discovery of Tiktaalik itself is a notable episode in the history of paleontology, since researchers specifically predicted where to search for a transitional fossil of roughly this kind based on the age of the rock layers most likely to contain it, then found a strong candidate within a few field seasons of searching in the predicted location in the Canadian Arctic. This kind of successful, targeted prediction is relatively rare in paleontology, where most major fossil discoveries happen through a combination of favorable geology and considerable luck, rather than a direct search for a specific, predicted transitional form. This is not, strictly, a story about predators moving onto land. It is a reminder that the pressures shaping this ocean, the need to escape, to find shelter, to reach shallow water where larger predators struggle to follow, are powerful enough to eventually push some lineages out of the water altogether. The armored terror of dunkleosteus, in an indirect way, may have contributed to exactly this kind of pressure, encouraging smaller, more vulnerable fish to seek refuge in shallows and tidal margins, where a 9-meter armored predator could not easily follow. The name dunkleosteus itself honors Dr. David Dunkel, a paleontologist who studied Cleveland shale specimens of the animal decades before more complete material allowed later researchers to refine earlier reconstructions. This kind of layered scientific history, one generation of researcher building carefully on the specimens and conclusions of the generation before, runs quietly beneath nearly every animal described across this entire account, even when the account itself has no room to name each contributor individually. Picture, for a moment, what it would mean to swim through this ocean without any of the protections later animals take for granted. The water is warm and often murky, clouded with sediment washed down from the young forests beginning to take root on nearby land. Visibility is poor enough that a dunkleosteus might close the distance to striking range before it is even seen clearly. There is no warning call, no shared signal among prey animals, only the sudden pressure change of a massive jaw opening nearby, followed by the suction that pulls smaller bodies toward it. Survival here depends less on any single defense than on probability being in the wrong place at the wrong moment, or, more often, simply not being there at all. The Devonian's dominance does not last indefinitely. Toward the end of the period, a series of extinction pulses, collectively known as the Late Devonian Extinction, occurring across a window of several million years rather than a single sudden event, devastates marine life around the world, with reef ecosystems and armored fish among the hardest hit. The precise causes remain debated among researchers, with proposed explanations including changes in ocean oxygen levels, volcanic activity, and the ecological disruption caused by the rapid spread of early forests on land, which may have altered nutrient runoff into the oceans in ways that triggered algal blooms and localized deoxygenation of coastal waters. Whatever the combination of causes, the placoderms as a group do not survive this crisis. Dunkleosteus and its relatives vanish from the fossil record entirely, bringing an end to one of the most heavily armored chapters in the ocean's long history. What replaces them, in the tens of millions of years that follow, will not rely on armor at all. The next generation of ocean predators takes a very different evolutionary path, one built not on plating and blades, but on cartilage, speed, and a body plan so effective that some of its descendants remain almost unchanged in the oceans of the present day. By this point in Earth's history, the continents have gathered into a single vast landmass known as Pangaea, surrounded by a single connected ocean. This arrangement has significant consequences for ocean circulation, reducing the diversity of coastal habitats available compared to a world with multiple separate continents, and concentrating much of the planet's shallow marine life along a smaller number of coastlines. When the volcanic and climatic crisis of the Permian-Triassic boundary strikes, This reduced diversity of habitat may have left marine life with fewer refuges to retreat into compared to extinctions occurring under different continental arrangements. A factor some researchers propose as part of the explanation for why this particular extinction proved so severe compared to others described in this account. 252 million years ago, the ocean experiences the worst crisis in its entire history. The event now called the Permian-Triassic extinction, often referred to simply as the Great Dying, removes an estimated 90% of marine species from the planet in a geological instant, a span of perhaps 60,000 years that, compressed against the scale of everything covered so far in this account, amounts to almost no time at all. Massive volcanic eruptions in what is now Siberia release enormous quantities of carbon dioxide and other gases into the atmosphere over an extended period, driving global temperatures upward, acidifying the oceans, and stripping large portions of the water column of the oxygen needed to sustain animal life. The predators of the previous chapters, the last surviving descendants of Devonian sharks, the diverse fish lineages that had spent tens of millions of years refining themselves in the aftermath of the placoderms, are reduced to a small fraction of their former diversity. Entire ecological categories vanish. Reef ecosystems collapse so completely that true reef building will not fully recover for millions of years afterward. Whatever comes next in the ocean's story must, in effect, be built again almost from the beginning, using whatever survivors happened to make it through. What makes the recovery from this particular extinction unusual, compared to the recoveries described earlier in this account, is where the next generation of apex predators comes from. Rather than emerging from existing marine lineages, the ocean's top predators, over the following tens of millions of years, descend from land animals, reptiles that had only recently established themselves on dry ground. Now turning back toward the water their distant ancestors had left behind. This return is not simple or immediate. It requires reptile bodies, built for breathing air and moving on legs, to be reshaped for a life spent almost entirely submerged. The ichthyosaurs are the most complete example of this transformation. Early forms, appearing in the early Triassic not long after the extinction's worst effects begin to ease, still resemble elongated lizards with slightly paddle-like limbs, retaining much of their terrestrial ancestry in their basic proportions. Within a remarkably short span of evolutionary time, later ichthyosaurs abandon almost every visible trace of that ancestry. Limbs become flippers, the tail develops a vertical fluke for propulsion, the body takes on a streamlined, torpedo-like shape that converges, independently, on almost the same design later adopted by dolphins, an unrelated lineage of mammals that will not exist for another 150 million years, arriving at a strikingly similar solution to the same basic problem of moving efficiently through water. The speed of this transformation, from a land-capable reptile to a fully committed swimmer within a few million years, ranks among the fastest major anatomical transitions documented anywhere in the fossil record covered by this account. Early Triassic ichthyosaur fossils show limbs still recognizable as legs, complete with distinct finger and toe bones, even as the surrounding soft tissue was clearly already being reshaped into a paddle-like structure suited to swimming rather than walking. By the Middle Triassic, only a few million years later, these individual digit bones have multiplied and flattened into the broad, fan-like paddle structure that will remain characteristic of ichthyosaurs for the remainder of their long history. Bone, it turns out, can be reorganized considerably faster than most observers might expect, provided the evolutionary pressure to do so is strong enough. Some ichthyosaurs reach sizes that rival or exceed anything the ocean has produced up to this point in the story. Shonosaurus, from the late Triassic, is estimated at lengths approaching 15 meters in some specimens, while more recent and even larger finds attributed to related ichthyosaur species have pushed estimates for the largest individuals of this general group toward 20 meters or more, rivaling the size of the largest whales in the modern ocean. These are not slow, sluggish giants either. Their large eyes, some of the biggest relative to body size of any vertebrate known, suggest active hunters capable of pursuing prey into deep or dim water, possibly even hunting at depths where sunlight barely penetrates. Alongside the ichthyosaurs, other reptile lineages are experimenting with their own versions of a return to the sea, producing a wider range of body shapes than the ichthyosaurs alone would suggest. The nothosaurs retain longer necks and more clearly reptilian limbs, resembling something between a modern seal and a crocodile, likely spending time both in water and hauled out along coastlines, not unlike a sea lion today. The placodonts take yet another approach entirely, developing broad, flattened teeth suited to crushing shellfish rather than piercing flesh. Some species even growing heavy, turtle-like shells for protection against the same predators that were, at the same time, driving the evolution of the ichthyosaurs into faster and larger forms. The placodonts offer a particularly clear example of what researchers call convergent evolution, in which unrelated lineages arrive independently at similar solutions to similar problems. Their heavy, turtle-like shells develop entirely separately from true turtles, which emerge as a distinct reptile lineage around this same broad period, but through a different evolutionary pathway entirely. Both groups, faced with similar pressures, the need for protection in a world full of larger, more heavily armed marine predators, arrive at broadly similar armored solutions, despite no close relationship between them. This same pattern of convergence will appear again later in this account, most notably in the strikingly similar body shapes eventually shared by ichthyosaurs and, tens of millions of years later, dolphins. This diversity matters because it illustrates something important about how recovery from mass extinction actually works. The ocean, emptied of its previous inhabitants, does not fill back up with a single dominant design. It fills with experiments, some successful over the long term, some not each one, testing a different combination of size, speed, defense, and diet against the conditions of a still recovering world. The ichthyosaurs, ultimately, proved to be the most successful and enduring of these experiments, persisting for well over 100 million years and adapting across multiple extinction pressures of their own along the way. Nothosaurs, in particular, illustrate how much variation existed even among reptiles pursuing a broadly similar coastal lifestyle. Some species were quite small, under a meter in length, likely hunting small fish and invertebrates in shallow tide pools, while others reached several meters, capable of tackling considerably larger prey along open coastlines. This range of sizes within a single family suggests a wide diversity of ecological niches available along Triassic coastlines, each nothosaur species carving out a slightly different living from the same general stretch of recovering, resource-rich water. It is worth pausing on what this return to the water actually represents. These are animals whose ancestors, at some point, made the difficult transition from water to land, developing lungs, limbs, and reproductive strategies suited to a life away from the ocean. Their descendants then reverse much of that transition, keeping the lungs ichthyosaurs breathe air and must surface regularly, in the manner of whales and dolphins rather than fish, while reshaping almost everything else about their bodies to suit an aquatic life. It is a strange kind of persistence, evolution circling back toward the water not because the land failed these animals, but because the ocean, freshly emptied by catastrophe, offered opportunities that a crowded, competitive terrestrial world did not. What these early ichthyosaurs actually hunted can be reconstructed, in part, through fossilized stomach contents and the shape of their teeth. Many species carry small, conical teeth suited to gripping soft-bodied prey such as squid-like cephalopods, which are abundant throughout Triassic seas and appear to have formed a major part of the ichthyosaur diet. Others, particularly among the larger species, develop more robust, blunter teeth suited to crushing shelled prey or tackling larger fish. This range of tooth shapes across a single broad group suggests a wide diversity of hunting styles existing side by side. Much as it did among the placoderms of the previous chapter, some ichthyosaurs built for chasing fast, evasive prey through open water. Others adapted for a slower, more methodical search along the seafloor or reef margins. The nothosaurs and placodonts occupy the shallower, coastal margins of this Triassic Ocean, a habitat distinct from the open water favored by the larger ichthyosaurs. This division of territory matters because it reduces direct competition between groups that might otherwise be forced into conflict over the same limited resources. A nothosaur patrolling a rocky Triassic coastline, snapping at fish sheltering among submerged boulders, is rarely competing directly with an ichthyosaur, pursuing cephalopods far offshore in open water. The recovering ocean, in effect, sorts its returning reptiles into separate rooms, each pursuing a different version of the same basic strategy without treading too heavily on its neighbors. It is easy, looking back from a great distance, to imagine this recovery as calm and orderly, each lineage quietly finding its place in a newly reopened ocean. The reality, as best as the fossil record allows it to be reconstructed, was almost certainly messier. Populations expand and contract unpredictably in the aftermath of a crisis this severe. Species that seem successful for a few million years vanish for reasons that remain unclear, while others that leave only a scattered fossil trail apparently persist for tens of millions of years without much visible change. The ocean's recovery from the Great Dying is less a single, clean narrative than an uneven, halting process, visible to us now only in fragments, pieced together from whatever happened to survive as stone. The pattern established by this recovery catastrophe, followed by a period of experimentation, followed eventually by the rise of one or two dominant lineages out of many competing possibilities, is not unique to the Triassic. It recurs, in modified form, after nearly every major extinction described in this account, including the one that will end the next chapter's story as well. Recognizing this pattern does not make any single extinction less severe or any single recovery less significant. It simply reveals that the ocean, across its full 4 billion year history, has developed something like a consistent process for rebuilding itself, however long that process ultimately takes. By the close of the Triassic period, roughly 201 million years ago, the ocean looks fundamentally different from the fish-dominated waters of the Devonian chapter. Reptiles, not fish, occupy many of the largest and most capable predatory roles, a state of affairs that will persist and intensify for well over 100 million years to come. The ichthyosaurs and their relatives are not the final form this reptilian return to the sea will take. However, as the Triassic gives way to the Jurassic, new lineages of marine reptile begin appearing, some destined to grow larger, more heavily armed, and considerably more capable of violence than anything described in this chapter. The age of the sea dragons is about to begin in earnest. The Jurassic Ocean, beginning around 201 million years ago, inherits the ichthyosaurs of the previous chapter, but does not stop there. Over the tens of millions of years that follow, an entirely different lineage of marine reptile rises alongside them, one built along a very different set of proportions and destined, in its most extreme forms, to produce some of the most heavily armed predators the ocean will ever hold. These are the plesiosaurs. And within this broader group, a specialized branch known as the pliosaurs will eventually take the title of apex predator across much of the Jurassic and into the Cretaceous that follows it. The swimming mechanics of long-necked plesiosaurs have themselves been the subject of considerable scientific debate, since their 4 equally sized paddle-like limbs represent a swimming arrangement with no clear equivalent among modern animals. Some researchers have proposed that plesiosaurs use their front and rear paddles in an alternating, underwater flying motion similar to that of a sea turtle or penguin, while others have suggested a more complex, semi-independent motion, allowing fine control over turning and stopping. useful for a predator that may have relied on precise, sudden strikes with its long neck rather than sustained high-speed pursuit. Either way, the arrangement appears to have been effective enough to persist, with only gradual refinement, for well over 100 million years across the plesiosaur lineage as a whole. Plesiosaurs, in their more familiar long-necked form, carry a body plan unlike almost anything that came before them: a broad barrel-shaped torso, 4 large paddle-like limbs used in a rowing motion unusual among swimming animals, and a neck that in some species stretches to extraordinary lengths, supported by dozens of vertebrae, where a typical reptile might have only a handful. This long neck design appears suited to a particular hunting strategy, allowing the head to dart forward and strike at nearby prey, while the bulkier body continues on a steadier, more predictable path through the water, functioning almost like a fishing lure attached to a slow-moving boat. The pliosaurs abandon the long neck almost entirely, favoring instead a shortened neck, a massive skull, and jaws lined with some of the largest conical teeth of any marine predator in this account so far. Pliosaurus, known from several described species across the late Jurassic, is estimated in some specimens to have reached lengths approaching 10 to 12 meters, with skulls alone measuring roughly 2 meters from front to back. Bite force estimates for the largest pliosaurs, calculated from skull structure and muscle attachment points, place them among the most powerful bites ever produced by any animal, aquatic or terrestrial, rivaling or exceeding even the estimates calculated for dunkleosteus in the earlier Devonian chapter of this account. Reconstructing exactly how these giant predators interacted with one another relies heavily on trace fossils, bite marks, healed injuries, and occasionally broken and regrown bone rather than any direct observation, since no soft tissue behavior can survive across this span of time. A puncture wound of a specific size and spacing, matched carefully against the tooth arrangement of a candidate predator, can suggest a specific attack, though establishing whether that attack was predatory, defensive, or the result of competition between rivals of the same species often remains uncertain. This kind of careful, evidence-based reconstruction, acknowledging what can and cannot be confidently claimed, applies just as much to the pliosaurs of this chapter as it does to every other predator described throughout this account. What makes the pliosaurs particularly effective as predators is not simply the size of their jaws, but the way those jaws are used. Fossil evidence, including bite marks preserved on the bones of other marine reptiles, suggests that some pliosaurs employed a shake-and-tear feeding strategy not unlike that of a modern crocodile, gripping prey and twisting violently to remove manageable pieces rather than swallowing an animal whole. Given the size difference implied by some of these bite marks, it appears that certain pliosaurs were capable of attacking prey nearly as large as themselves, including other marine reptiles that, in an earlier era, might have expected to occupy the top of the food chain without serious challenge. Sharks, meanwhile, have not disappeared from this ocean, even as reptiles dominate its largest predatory roles. Hybodont sharks, distant relatives of modern sharks, remain common throughout Jurassic seas, generally occupying smaller-bodied predatory niches rather than competing directly with the largest plesiosaurs and pliosaurs. This coexistence reptiles above, sharks and bony fish filling out the remaining space, will persist through the Jurassic and into the Cretaceous period that follows it, though the balance of power between different predator groups continues shifting as new species arrive and old ones vanish. The ichthyosaurs, dominant for so much of the Triassic and early Jurassic, begin a slow decline through the later Jurassic and into the Cretaceous, though the reasons remain only partly understood. Competition from the rising plesiosaurs and pliosaurs may account for part of this decline, as these newer predators encroach on similar prey and similar open water habitats. Changes in the availability of the cephalopod prey many ichthyosaurs relied upon may account for another part. Whatever the precise combination of causes, the the group that once produced some of the largest marine predators in this entire account grows steadily rarer, its once wide diversity narrowing to a smaller number of surviving lineages by the time the Cretaceous period is fully underway. This kind of gradual replacement, one dominant lineage easing into decline while another rises to take its place, without any single dramatic event forcing the transition, appears repeatedly throughout the ocean's history. And it is worth noting as a contrast to the sudden, catastrophic transitions described in earlier chapters. Not every shift in the ocean's cast of predators requires an extinction event. Sometimes one group simply outcompetes another, slowly, over millions of years, until the losing lineage fades from the fossil record almost quietly, its disappearance more a matter of accumulated disadvantage than any single crisis. As the Cretaceous period begins, roughly 145 million years ago, a new group of marine reptiles enters the story, one that will eventually rival and, by some measures, surpass the pliosaurs in size and predatory reach. The mosasaurs begin as relatively modest, lizard-like marine hunters, closely related to modern monitor lizards and snakes, but within a span of roughly 20 million years, they diversify explosively, producing a wide range of body sizes and hunting strategies that come to dominate late Cretaceous seas almost entirely. Mosasaurus, the largest and most famous member of this group, reaches estimated lengths of up to 17 meters in the largest specimens, powered by a long, muscular tail and steered by 4 paddle-like limbs adapted from an ancestral lizard's legs. Its jaws carry a double row of recurved teeth, and unusually, mosasaurs also possess a second set of teeth on the roof of the mouth, an adaptation shared with modern snakes that helps prevent struggling prey from escaping once caught. Fossil stomach contents attributed to mosasaurs include fish, ammonites, smaller marine reptiles, and even other mosasaurs, painting a picture of an animal willing to attack nearly anything within reach, provided it could be overpowered. The geography of the late Cretaceous ocean also plays a role in this story. A shallow inland seaway divides North America into 2 separate landmasses during this period, creating an enormous expanse of warm, food-rich water that supports an unusually dense concentration of mosasaurs, giant fish, and other marine predators, many of which are known today primarily from fossil deposits along the seaway's former margins in present-day Kansas and neighboring states. This single body of water, now long vanished as the continent reassembled into its current form, preserves one of the most complete pictures available anywhere of a fully realized late Cretaceous marine ecosystem. Predators and prey alike captured together in the same rock formations. Tylosaurus, a slightly more elongated mosasaur genus, known primarily from North American deposits, appears to have specialized in a somewhat different diet, with preserved stomach contents including diving birds, smaller marine reptiles, and even the bones of land animals that had, for whatever reason, ended up in the water. This willingness to consume almost any available prey, rather than specializing narrowly, may have contributed to the rapid success and wide geographic spread of mosasaurs during the final tens of millions of years of the Cretaceous period, allowing them to occupy nearly every marine ecosystem across the globe. Ammonites, coiled-shelled relatives of modern nautilus, are extraordinarily abundant throughout Jurassic and Cretaceous seas, and their shells provide an unusually clear record of predation pressure through this entire period. Many ammonite fossils preserve circular or crescent-shaped puncture damage, matching the tooth spacing of specific mosasaur species, allowing researchers to identify not only that predation occurred, but, in some cases, roughly which predator was responsible. This abundance of shelled prey likely shaped the blunter, crushing teeth seen in some mosasaur lineages, distinct from the sharper, piercing teeth favored by mosasaurs that specialize more heavily on fish and other soft-bodied prey. The diversity of mosasaur tooth shapes across different genera reflects, in large part, a diversity of favored prey. each lineage refining its bite to match whatever food source it relied upon most heavily. Sharks, too, reach new extremes of size and capability during this same period. Cretoxorhina, sometimes nicknamed the Ginsu shark by paleontologists studying its remarkably sharp, serrated teeth, grows to lengths estimated between 6 and 7 meters, rivaling the size of the modern great white shark, while occupying a broadly similar ecological role as a fast, active pursuit predator. Fossil evidence places Cretoxorhina in direct competition and occasionally direct conflict with mosasaurs of similar size, including at least one famous specimen preserving what appear to be shark bite marks on mosasaur bone, alongside evidence suggesting the reverse encounter occurred as well. Xiphactinus, though not a shark but a large predatory bony fish, adds yet another layer of danger to this Cretaceous ocean. Reaching lengths of up to 6 meters, with an upturned jaw lined with long, fang-like teeth, Xiphactinus hunted through a combination of speed and aggression that occasionally proved fatal, even to itself. One of the most famous fossils in the history of paleontology preserves a Xiphactinus with the intact skeleton of another large fish, nearly 2 meters long, inside its rib cage, apparently swallowed whole shortly before both animals died. Likely from complications related to the sheer size of the meal Xiphactinus had attempted to consume. This layered ocean pliosaurs giving way to mosasaurs, ichthyosaurs persisting alongside both for a time before eventually declining, sharks and giant bony fish filling in whatever space remains, represents one of the most predator-dense periods in the entire history covered by this account. Nearly every available ecological role, from ambush hunter to open water pursuit predator to opportunistic scavenger, is occupied by something built specifically to fill it, often by more than one competing lineage at once. It is difficult to imagine a more thoroughly dangerous ocean than the one that exists across the final tens of millions of years of the Cretaceous period. None of it lasts. 66 million years ago, an asteroid roughly 10 kilometers across strikes what is now the Yucatan Peninsula, triggering a cascade of environmental collapse that ends the Cretaceous period and, with it, the age of the great marine reptiles described in this chapter. Mosasaurs, plesiosaurs, and the last of the pliosaur lineages do not survive this event. Their disappearance is not gradual, in the way earlier extinctions in this account have sometimes unfolded over hundreds of thousands or millions of years. It arrives, geologically speaking, almost overnight, ending more than 130 million years of reptilian dominance over the ocean's largest predatory roles. What survives this catastrophe, and what eventually rises to fill the enormous vacancy left behind, belongs to a lineage that, up to this point in the story, has played almost no role in the ocean at all. 66 million years ago, in the immediate aftermath of the asteroid strike that closes the previous chapter, the ocean is a strange and empty place. The mosasaurs are gone. The last plesiosaurs are gone. Entire categories of large predator vanish within what is, geologically, a single moment, leaving behind an ocean with far fewer serious threats than it has held at almost any point since the Devonian. Surviving fish, sharks that made it through the crisis, and a scattering of smaller marine reptiles inherit a world with considerably more room in it than existed the day before the impact. Whales are not the only mammal lineage to attempt to return to the water during this general span of Earth's history, though they are by far the most complete example. Early relatives of manatees and dugongs make a similar transition around roughly the same broad period, favoring slow-moving, plant-eating lifestyles in shallow coastal water rather than active predation. Later still, ancestors of seals and sea lions will make their own, separate return toward the ocean, retaining a stronger connection to land than whales ultimately do. Each of these transitions happens independently, driven by unrelated lineages facing broadly similar opportunities in a world where ocean habitats, emptied by extinction or simply underused by existing marine animals, offered advantages substantial enough to justify giving up the comparative safety of solid ground. Into this emptiness, over the following 10 million years, a group of land mammals begins a transition that will eventually produce some of the most capable ocean predators this account describes. The earliest of these animals, exemplified by a genus called Pakicetus, look almost nothing like a whale, roughly the size of a large dog, with 4 legs and a build resembling a long-snouted wolf more than anything aquatic. Pakicetus lives along rivers and shorelines in what is now South Asia, likely wading into shallow water to hunt fish while still spending much of its life on land. Nothing about its skeleton suggests the scale of transformation that its descendants are about to undergo. Within a remarkably short span of evolutionary time, perhaps 8 to 10 million years, fast by the standards of most major transitions described in this account, descendants of animals like Pakicetus move decisively into the water. Ambulocetus, sometimes described as a walking whale, retains 4 functional limbs, but hunts primarily in water, likely ambushing prey from the shallows in a manner not unlike a modern crocodile. Rhodochesis, somewhat later, shows limbs increasingly modified for swimming rather than walking, with a tail beginning to take on the flattened, propulsive shape that will define every whale that follows. Each of these intermediate forms represents a real, functioning animal, not a theoretical stepping stone, well adapted to the particular mix of water and land available to it at the time. The transition documented across Pakicetus, Ambulocetus, and Rhodocetus did not happen in isolation from the rest of the Eocene ocean. Sea levels during this period are notably high, flooding low-lying coastal regions across much of the world and creating exactly the kind of shallow, sheltered waterways where a land mammal experimenting with an aquatic lifestyle could establish itself without immediately competing against the largest open ocean predators of the time. This favorable coastal geography may have played as large a role in the whale lineage's early success as any single anatomical adaptation, offering a relatively low-risk environment in which each intermediate step of the transition could be tested. By the middle of the Eocene, roughly 45 to 35 million years ago, this transition produces Basilosaurus, an animal that finally abandons any meaningful connection to land, reaching lengths of up to 18 meters. Though notably slender and serpentine rather than bulky, Basilosaurus swims through warm Eocene seas, using powerful undulations of its long body. Its name meaning king lizard, a product of early paleontologists, mistaking its remains for those of a giant marine reptile, rather than recognizing it as an early whale. Vestigial hind limbs remain, tiny and functionally useless for locomotion, a visible remnant of the 4-legged ancestors only a few million years removed. The history of how Basilosaurus was first identified says something useful about how easily deep time can be misread from fragmentary evidence. When its bones were first uncovered in the southern United States in the early 19th century, they were assembled and displayed for a time as the remains of a giant sea serpent, an interpretation that fit contemporary expectations about what an enormous, elongated marine skeleton ought to represent. It took further study and comparison with other early whale fossils discovered later to correctly identify Basilosaurus as a mammal rather than a reptile. This early misidentification is a reminder that even careful observers, working with real physical evidence, can arrive at a plausible but ultimately incorrect interpretation when the available context is still incomplete. A caution worth carrying into any discussion of unusual remains recovered from the ocean, whether ancient or modern. Basilosaurus is, by most reconstructions, an active and capable predator, its jaws lined with teeth suited to both piercing and shearing prey, a dental arrangement inherited from its terrestrial carnivorous ancestors rather than developed fresh for aquatic life. Fossil evidence, including bite-marked skulls of smaller early whales found in the same rock formations, suggests that Basilosaurus preyed at least occasionally on other whales, including Dorodon, a smaller relative living alongside it in the same Eocene seas. This is worth noting, because it establishes something that will matter greatly in the chapters ahead. Whales, from a very early point in their evolutionary history, are not simply prey animals waiting to be hunted by sharks and reptiles. Some of them are predators in their own right, and a few, as later chapters will show, become the most capable ocean predators of any era. Dorudon itself deserves a closer look, since its relationship to Basilosaurus illustrates how quickly a predator-prey dynamic can establish itself within a single emerging lineage. Smaller than Basilosaurus, at roughly 5 meters in length, Dorudon shares many of the same anatomical adaptations for aquatic life, including a similarly serpentine body and reduced hind limbs. Multiple Dorudon fossils recovered from Eocene deposits in Egypt show puncture marks consistent with the tooth spacing of Basilosaurus, alongside evidence that juvenile Dorudon in particular may have been targeted, a pattern not unlike the size-selective predation seen among some modern marine mammals, within less than 10 million years of the earliest whales entering the water. In other words, whales are already preying on other whales, a behavior that persists in modified form among certain toothed whale species to the present day. The resemblance between early whales and the ichthyosaurs described several chapters earlier in this account is worth pausing on, since the two lineages arrive at broadly similar streamlined body shapes from opposite directions in time and from entirely unrelated ancestors. Ichthyosaurs begin as land reptiles moving toward the water in the Triassic, tens of millions of years before whales make a nearly identical transition from an entirely separate group of land mammals. Neither lineage copies the other. Both are simply responding to the same physical demands of moving efficiently through water, arriving independently and roughly 150 million years apart, at a body plan that a casual observer might easily mistake for evidence of a shared ancestry that does not, in fact, exist. Sharks, meanwhile, continue their own quiet persistence through this same period, having survived the extinction that ended the previous chapter with considerably less disruption than the marine reptiles suffered. Freed from competition with mosasaurs and pliosaurs, shark lineages diversify steadily through the Paleocene and Eocene, though none yet approach the scale that later chapters will describe. This is, in a sense, a rebuilding period for the ocean's predators, generally whales, establishing an entirely new lineage of marine hunter. Sharks quietly expanding into ecological space left vacant by the extinction. Both groups laying groundwork for a far more dramatic confrontation, still tens of millions of years in the future. The origin of filter feeding itself, the strategy that will eventually allow baleen whales to become the largest animals in the history of this planet, appears to develop gradually rather than as a sudden innovation. Early baleen whale ancestors retained functional teeth well into their evolutionary history, and some transitional fossils show a combination of teeth and the beginnings of the fibrous baleen plates that fully filter-feeding whales rely on today, suggesting a period during which some species may have used both strategies depending on the prey available. This transition from active, tooth-based hunting toward passive filtering of enormous quantities of small prey represents one of the more unusual dietary shifts documented anywhere in this account, trading the capabilities of a predator for an entirely different and ultimately far more productive way of extracting food from the ocean. As the Eocene gives way to the Oligocene, roughly 34 million years ago, global cooling begins reshaping ocean currents and circulation patterns in ways that will influence the rest of this account significantly. The opening of deep water passages around Antarctica, as the southern continents finish separating from one another, allows a cold circumpolar current to form, isolating Antarctica thermally and triggering a period of global cooling that changes which predators can thrive and where. Basilosaurus and its close relatives do not survive this transition in their original form, though their descendants, early relatives of both toothed and baleen whales, continue diversifying through the cooler waters that follow. The senses available to these early whales also shift considerably, as the transition from land to water proceeds. Land-dwelling ancestors relied heavily on smell and airborne hearing, senses poorly suited to an environment where scent disperses differently and where sound travels through water in ways very different from through air. Later, whale lineages compensate for this by developing echolocation, a form of biological sonar that allows some toothed whales to construct a detailed picture of their surroundings using sound alone, useful in murky water or at depths where light barely reaches. This sensory shift does not appear immediately in animals like Basilosaurus, but the early groundwork for it is already present in the inner ear structures of these Eocene whales, refined further in the tens of millions of years to come. It is worth pausing here to consider what this whale lineage represents in the broader story this documentary is telling. Every predator described in the chapters before this one, from Anomalocaris through Dunkleosteus, from the ichthyosaurs through the mosasaurus, descends from an ancestor that never left the water at all, or that left it only briefly before turning back, as the marine reptiles did in the Triassic. Whales take a different path entirely. Their ancestors commit fully to life on land for tens of millions of years, developing lungs, limbs, and a mammalian metabolism entirely unsuited to permanent aquatic life, before turning back toward the ocean and reshaping nearly every part of that inheritance to fit a world of open water. It is, in its own way, one of the more improbable transformations in the entire history of this planet's oceans, and it sets the stage for a lineage that will eventually produce predators rivaling anything described so far in this account. This same cooling period also marks the point where baleen whales and toothed whales begin to diverge more clearly along separate evolutionary paths, one group specializing toward filter feeding on small prey in enormous quantities, the other retaining and refining the predatory habits already visible in animals like Basilosaurus and Dorudon. It is this second group, the toothed whales, that will matter most for the remainder of this chapter's story, since their descendants eventually produce a predator capable of challenging even the largest sharks the ocean has yet to produce. The cooling oceans of the Oligocene and early Miocene are not yet finished producing new predators. Somewhere in these changing waters, both whales and sharks are approaching a size and capability that will bring them into direct, violent competition with one another in an ocean rapidly filling with more large prey than it has held in tens of millions of years. By the early Miocene, roughly 23 million years ago, the ocean has spent tens of millions of years quietly rebuilding itself in the wake of the extinction that closed the age of the great marine reptiles. Whales, descended from the land mammals described in the previous chapter, have diversified considerably, producing both filter-feeding giants and a range of smaller, toothed hunters. Sharks, having weathered that same extinction with comparatively little disruption, have continued their own long refinement, and somewhere within this refinement, a lineage is approaching a size that will make it the largest predatory shark this planet has ever produced. Otodus megalodon, commonly known simply as megalodon, does not appear suddenly. It descends from a long lineage of large-toothed sharks stretching back tens of millions of years, each generation growing marginally larger and better equipped to prey on the whales that were, at the same time, growing more numerous and more varied in Miocene seas. By the time megalodon reaches its full size, most estimates place adult individuals somewhere between 15 and 20 meters in length, though the exact upper limit remains debated among researchers. Since megalodon, like all sharks, has a skeleton made primarily of cartilage rather than bone, a material that rarely survives long enough to fossilize completely. Estimating a shark's total length from tooth measurements alone requires comparison with the tooth-to-body proportions of living sharks with similar dental structure. Primarily the great white shark, since no complete megalodon skeleton has ever been recovered. This method carries inherent uncertainty, since it assumes megalodon's overall body proportions resembled those of its modern relative closely enough for the comparison to hold, an assumption that cannot be verified directly without more complete remains. Some researchers have proposed alternative body proportions based on the shape of megalodon vertebrae, which occasionally do fossilize due to their higher mineral content compared to the rest of the shark's cartilaginous skeleton, and these alternative models have produced somewhat different length estimates than the tooth-based method alone. The true upper limit of megalodon's size, therefore, remains an active area of paleontological research rather than a settled figure. What to survive, in enormous quantities, are megalodon's teeth serrated, triangular, and in the largest known specimens, measuring close to 18 centimeters along their longest edge. These teeth, combined with the size of fossilized shark vertebrae recovered from various sites around the world, allow researchers to estimate not only megalodon's length but also its bite force, which calculations place among the strongest of any predator, living or extinct, rivaling and by some estimates exceeding even the bite forces attributed to dunkleosteus and the largest pliosaurs described in earlier chapters of this account. Megalodon teeth are, today, among the most commonly recovered large fossils anywhere in the world, turning up in marine sediments across every continent except Antarctica, a distribution that reflects both the species' wide historical range and the simple fact that sharks continuously shed and replace their teeth throughout their lives, producing thousands of teeth per individual over a lifetime, rather than the single set most vertebrates are limited to. This constant replacement means the fossil record for megalodon's teeth is unusually rich compared to the skeletal record for almost any other predator described in this account, even though not one complete megalodon skeleton has ever been recovered anywhere. Fossil evidence of megalodon's diet comes primarily from bite marks preserved on whale bones recovered from Miocene and Pliocene deposits worldwide. These marks show clear evidence of an animal capable of biting directly through the vertebrae and ribs of whales, considerably larger than any modern shark would attempt to attack, suggesting that megalodons specialized, at least in part, on the whale populations that had become abundant during this same period. Some researchers have proposed that megalodon's feeding strategy may have shifted with age, with younger individuals targeting smaller prey such as fish and seals in shallower nursery habitats, while fully grown adults moved into deeper, open water to hunt whales directly, a pattern documented in several nursery-like fossil sites where juvenile megalodon teeth are found in unusually high concentration. Several fossil sites around the world, including locations in what is now Panama, Spain, and the southeastern United States, preserve unusually dense concentrations of smaller megalodon teeth, alongside the remains of juvenile whales and other moderate-sized marine animals, evidence that has led researchers to identify these as probable nursery grounds. The presence of shallow, warm, sheltered water at each of these sites, combined with the apparent absence of adult-sized megalodon remains in the same deposits, suggests a deliberate separation between where megalodon gave birth and raised young and where fully grown adults hunted. This kind of nursery behavior is documented among several living shark species today, and its likely presence in megalodon suggests a reproductive strategy already well established tens of millions of years before the present. Megalodon does not have this ocean entirely to itself, however. As the Miocene progresses, toothed whales continue diversifying, and among them, a predator emerges that appears to have rivaled megalodon directly for the position of apex predator in at least some regions of the Miocene Ocean. Leviathan melvillei, known from a skull recovered in Peru and named partly in reference to the whale from Herman Melville's novel, is estimated to have reached lengths of 13 to 17 meters, roughly comparable to a large modern sperm whale, but equipped with a set of teeth utterly unlike anything a modern sperm whale possesses. Where modern sperm whales carry teeth only in their lower jaw, suited mainly to gripping soft-bodied prey such as squid, Leviathan's teeth appear in both upper and lower jaws, reaching lengths of up to 36 centimeters, including the root, among the largest functional teeth of any predator known to have existed. This dental arrangement suggests an animal built specifically for hunting large prey through direct bites rather than suction feeding, likely including other whales, in direct ecological competition with megalodon over broadly similar prey across at least part of the Miocene Ocean. The skull of Leviathan also shows evidence of an unusually large space likely occupied in life by a spermaceti organ, similar to that found in modern sperm whales, though its exact function in Leviathan remains debated. In modern sperm whales, this organ appears to play a role in sound production and possibly in buoyancy control, though its use as a ramming weapon has also been proposed for both modern and extinct species. Whatever its precise function, the combination of a powerful bite, an unusually large head, and a body size rivaling the largest toothed predators of its era suggests Leviathan was capable of tackling prey that few other animals in the Miocene Ocean would have dared approach. Whether Leviathan and megalodon ever competed directly in the same waters, and what the outcome of any such encounter might have looked like, remains a matter of informed speculation rather than settled fact, since the fossil record does not preserve direct evidence of interaction between the two. What is reasonably well established is that both predators existed during overlapping periods of the Miocene. Both relied at least partly on whale prey, and both represent, in their own way, an extreme endpoint of the evolutionary pressures traced throughout this entire account: bone and cartilage, mammal and fish, arriving independently at broadly similar solutions to the problem of how to become the largest, most capable predator available in a given ocean. The Miocene Ocean that supports both of these giants is warmer and richer in productivity than the oceans that come immediately before or after it, supporting large populations of baleen whales and other prey animals, substantial enough to sustain predators of this scale. This abundance does not last indefinitely. Beginning in the late Miocene and continuing into the Pliocene, global cooling once again reshapes ocean conditions, altering current patterns and reducing the productivity of some coastal regions that had previously supported large whale populations. Several whale lineages that megalodon likely depended on for prey decline or shift their ranges during this period, removing a significant portion of the food base that had supported the largest sharks in the ocean's history. Megalodon holds an unusual place in the modern imagination, having become, through documentaries and popular fiction, one of the most widely recognized extinct predators this planet has ever produced, occasionally accompanied by speculation that it might still survive undetected in the deepest parts of the modern ocean. The scientific evidence does not support this idea. Megalodon relied heavily on warm, shallow coastal nursery habitats that leave a distinctive geological signature, and no comparable modern nursery evidence has ever been found. It fed on whale species whose modern population patterns and migratory routes are well documented and closely monitored, and no unexplained pattern of predation consistent with an active megalodon population has ever been recorded. Separating this kind of grounded, evidence-based account from more speculative claims matters, not because the true story of megalodon is any less compelling without the speculation, but because the actual fossil record already tells a genuinely striking story on its own terms. At roughly the same time, a new competitor enters the picture, one that, unlike megalodon or Leviathan, survives into the present day. Early orcas and other social, intelligent toothed whales begin expanding through the late Miocene and Pliocene oceans, hunting cooperatively in ways that neither megalodon nor Leviathan appear to have been capable of. A single, solitary predator, however large, may struggle to compete against coordinated groups capable of encircling and exhausting prey through teamwork rather than raw individual size. This is speculative, since direct behavioral evidence for extinct animals is impossible to obtain directly, but it represents one plausible thread among several proposed to explain what happens next. By roughly 3.5 million years ago, megalodon disappears from the fossil record entirely. The causes appear to be numerous rather than singular: cooling oceans, declining prey populations, competition from increasingly capable and social whale predators, and possibly changes in sea level that reduce the shallow coastal nursery habitats megalodon's juveniles appear to have relied upon. No single event ends the reign of the largest predatory shark this ocean has ever produced. Instead, a combination of gradual pressures, accumulating over a few million years, achieves what no single predator or catastrophe could manage on its own. What remains, in the tens of millions of years between megalodon's disappearance and the present day, is an ocean that continues refining its predators without pause. Even as the largest and most extreme forms described in this account have already come and gone. The story does not end with megalodon. It simply moves into an ocean that, in the present day, remains far less explored and far less understood than most people assume. The ocean of the present day is, by most measures, less understood than the surface of the Moon or Mars. More than 80% of it remains unmapped in any meaningful detail, and the deep sea in particular, the vast, lightless region beginning roughly 200 meters below the surface and extending to the ocean's greatest depths, has been directly observed by humans in only the smallest fraction of its total volume. This is worth sitting with plainly. Every predator described in this account so far comes to us through fossils, through stone that has had millions of years to form and to be discovered. The modern deep ocean does not require fossils to remain mysterious. It is mysterious simply because almost no one has been there to look. What has been observed in the parts of the deep ocean humans have managed to explore suggests an environment that produces its own kind of extremity, quite separate from anything driven by the mass extinctions and recoveries described in earlier chapters. Deep-sea gigantism, a pattern in which certain deep-water species grow considerably larger than their shallow-water relatives, appears repeatedly across unrelated groups of animals. Giant isopods, distant relatives of the small pill bugs found in gardens on land, grow to the size of a house cat in the cold, high-pressure water of the deep sea floor. Giant squid, for centuries known only through occasional carcasses washed ashore or recovered from the stomachs of sperm whales, were not filmed alive in their natural deep-water habitat until relatively recently, despite reaching lengths of up to 12 or 13 meters, including their long feeding tentacles. Bioluminescence, the biological production of light, appears far more widely across deep-sea animals than most people outside marine biology tend to realize, evolving independently dozens of separate times across entirely unrelated groups of fish, squid, jellyfish, and even some sharks. In a permanently dark environment, light becomes a tool that can serve almost any purpose, ordinarily served by color, sound, or scent. In a lit environment, a lure to attract prey, as with the anglerfish, a flash used to startle or confuse a predator, or a signal used to locate a potential mate across the vast, empty distances of open deep water. Some deep-sea sharks are now known to glow faintly along their bodies, a discovery made only within recent years using specialized low-light cameras, a reminder that even something as fundamental as whether a given species produces its own light has, for many deep-sea animals, only recently become known to science at all. The relationship between giant squid and sperm whales deserves particular attention here, since it represents one of the few predator confrontations in this entire account that continues, largely unwitnessed, in the present day. Sperm whales dive to depths exceeding 1,000 meters in pursuit of giant and colossal squid, and many recovered whale specimens carry circular scars across their skin, left by the suction cups and hooked rings of squid tentacles during struggles that no human has ever directly observed. Colossal squid, a separate and even larger species found primarily in the cold waters around Antarctica, are estimated to reach lengths comparable to or exceeding the giant squid, equipped with swiveling hooks on their tentacles, in addition to suckers, though even less is known about their behavior than that of their slightly better studied relative. Beyond squid and whales, the deep ocean supports its own resident community of predators built specifically for hunting in permanent darkness under crushing pressure. Anglerfish carry a modified spine tipped with a small, bioluminescent lure, dangled in front of an oversized mouth capable of swallowing prey larger than the anglerfish's own body, an adaptation suited to an environment where meals arrive rarely and cannot be allowed to escape once found. The gulper eel takes a similar approach to an extreme conclusion. Its jaw hinged so widely that it can engulf prey considerably larger than its own slender body, an entire feeding strategy built around the assumption that another meal may not come along for a long while. These are not animals competing for the kind of dominance megalodon or Leviathan once held. They occupy a different kind of ocean altogether, one where scarcity, rather than competition between giants, shapes almost every visible adaptation. Whale falls add yet another layer to this deep, dark ecosystem. When a whale dies and its body sinks to the seafloor, it creates a sudden, concentrated source of food in an environment that is otherwise extremely food poor, supporting a succession of scavengers and specialized organisms that can persist around a single carcass for decades. Sleeper sharks, deep-sea worms adapted specifically to feeding on whalebone, and a range of other opportunistic animals gather around these falls in numbers and diversity that surprise the researchers who first documented the phenomenon by submersible. It is a reminder that even in the most food-scarce regions of the planet, a single large body, whether from a predator or a filter feeder, can sustain an entire hidden community for longer than most human structures remain standing on land. Sharks, too, continue producing surprises drawn from the deep ocean's unexplored margins. The megamouth shark, a large filter-feeding species reaching lengths of over 5 meters, was entirely unknown to science until 1976, when one was accidentally caught near Hawaii, having spent an unknown but presumably long span of time living in deep water without ever being documented. The frilled shark, a slender, eel-like predator with rows of needle-like teeth arranged for gripping soft-bodied prey such as squid, retains a body plan that closely resembles shark fossils tens of millions of years old, leading some researchers to describe it informally as a living fossil, a species that appears to have changed remarkably little while the ocean around it transformed repeatedly through the events described in this account. Much of what has been learned about the deep ocean in recent decades comes from technology that did not exist for most of human history. Remotely operated vehicles, capable of descending to extreme depths while transmitting live video to researchers on the surface, have only been in regular scientific use since the latter part of the 20th century, and crude submersibles, capable of reaching the very deepest trenches, remain few in number even today, with each full-depth expedition representing a significant undertaking in both engineering and cost. Every new deep-sea expedition using this technology tends to document at least some organisms never previously recorded, a track record that is held consistently enough that researchers now treat the discovery of unfamiliar deep-sea life as an expected outcome of exploration rather than a rare surprise. The honest scientific position on what else might exist in the least explored portions of the deep ocean is one of genuine uncertainty rather than either confident denial or unfounded speculation. New species continue to be described from deep-sea expeditions at a steady rate, including, in recent decades, animals previously known only from partial remains or reported sightings that had not yet been confirmed through direct observation. This does not mean that every unconfirmed report from the deep ocean reflects an undiscovered predator waiting to be found. It means, more modestly, that the deep ocean has repeatedly demonstrated its capacity to hold animals that remained entirely unknown until very recently. And there is no particular reason to assume that this capacity has been exhausted. Some of the more persistent reports from deep or open ocean regions, unusual sonar contacts, carcasses too decomposed to identify with confidence, occasional sightings reported by fishing crews and sailors that do not clearly match any known species remain unresolved rather than explained. Scientists who study these reports generally treat them the way any careful researcher treats an incomplete data set, neither dismissing them outright nor treating them as confirmed evidence of anything specific. The honest answer, in the vast majority of these cases, is that the available evidence is not sufficient to draw a firm conclusion in either direction, and further investigation, if it ever occurs, would be required before any confident claim could be made. This steady rate of discovery is worth holding in perspective against everything described earlier in this account. Every predator from the Cambrian through the Miocene reached us only after being extinct for millions of years, identified entirely through the patient work of paleontologists piecing together stone. The deep ocean offers something different, the possibility, however modest, of encountering a genuinely new form of life that is not extinct at all, simply unfound until the right expedition happens to look in the right place. That possibility does not require any embellishment to feel significant. It is already, on its own terms, one of the more striking facts about the ocean covered in this entire account. What can be said with more confidence is that the deep ocean continues to operate under the same basic evolutionary pressures traced throughout this entire account. Prey must avoid being eaten. Predators must find enough food to survive and reproduce. Pressure, darkness, cold, and scarcity of food shape deep-sea bodies in the present day, just as oxygen levels, temperature, and available prey shape the bodies described in every previous chapter of this documentary. There is no reason to think this pattern has paused simply because it has moved into water too deep and too dark for direct observation. If anything, the deep ocean represents the pattern's most recent frontier, still actively working, still producing outcomes that have not yet been fully cataloged or understood. Vampire squid, despite their name, are neither vampires nor true squid in the strictest sense, occupying a small evolutionary branch of their own between squid and octopus. Living in the oxygen-poor middle depths of the ocean, they have developed a slow, low-energy metabolism suited to a life spent mostly drifting rather than actively pursuing prey, feeding largely on marine debris drifting down from above rather than hunting living animals directly. Their presence in this account is less about danger and more about range, a reminder that the deep ocean does not produce only extreme predators. It also produces extreme conservation of energy, extreme patience, and extreme tolerance for conditions that would be lethal to almost anything living closer to the surface. It is also worth remembering that scale itself has never been a fixed feature of this ocean. The same stretch of water that produced a meter-long anomalocaris in the Cambrian, when oxygen was scarce and true predators were still a new idea, later produced a 17-meter mosasaurus, once conditions allowed for it, and later still nearly emptied itself of large predators, entirely before refilling with whales and sharks of its own considerable size. Whatever the deep ocean is quietly assembling in the present day will be shaped, as everything before it was shaped, by the particular chemistry, temperature, and pressure of this current moment in the planet's very long history. Consider, for a moment, the scale of what remains unmapped. The Mariana Trench, the deepest known point in any ocean, plunges to nearly 11,000 meters below the surface, a depth greater than Mount Everest is tall, and only a small number of crude descents have ever reached its deepest point. Between the surface and that extreme depth lies an almost unimaginable volume of water, layered into distinct zones by temperature, pressure, and available light, each zone home to its own communities of animals, many of which remain undescribed. Entire mountain ranges exist on the ocean floor, unmapped in detail, potentially hosting ecosystems as distinct and specialized as anything found on an isolated island on land. None of this requires exaggeration to be genuinely difficult to sit with in the dark. The ocean that produced Anomalocaris, Dunkleosteus, the ichthyosaurs, the mosasaurs, megalodon, and Leviathan has not stopped producing new forms simply because this account is nearing its end. It continues. In water most people will never see. Under pressure, most human bodies could not survive unassisted, following rules that have not changed in any fundamental sense since the first true predator closed its mouth around the first true prey, nearly 541 million years ago. What that ocean is producing right now, in its least explored corners, remains, quite honestly, an open question. Nearly 4 billion years separate the still, lifeless water described at the beginning of this account from the ocean that exists today. An ocean that remains, in its deepest and darkest regions, only partly known, even now. Across that span of time, this same body of water has produced armored arthropods the size of a small car, fish with jaws capable of biting through bone, reptiles that return to the sea their ancestors once left, sharks larger than any predator alive today, and whales that became hunters as capable as anything they might once have feared. None of it was built with malice. All of it was built, generation after generation, by the same simple pressure: survive one more day, one more season, one more year, whatever the water demanded in exchange. The word nightmare, which this account has used more than once, belongs entirely to us. It reflects the distance between a human nervous system, built to fear teeth and darkness and the unknown, and an ocean that has never once needed anyone to be afraid of it in order to keep functioning exactly as it always has. Every animal described across these chapters was simply attempting to eat, to avoid being eaten, and to pass its particular combination of traits forward into the next generation, an ambition no different, in its basic shape, from that of a garden spider or a house cat. Scale and unfamiliarity are what make dunkleosteus or megalodon feel like something closer to horror than to biology. The underlying mechanism is the same mechanism operating in every living thing, including the animal reading or listening to these words right now. What remains, at the far end of this account, is not a conclusion so much as an ongoing situation. The deep ocean has not stopped producing new forms, simply because this documentary has reached its final chapter. Somewhere in water most people will never see, under pressure most bodies could not survive. The same pattern that produced every predator described tonight continues its slow, patient work, refining shapes according to rules that have not meaningfully changed since the Cambrian seas first learned to bite. What that work is producing right now is not fully known, and it may not be fully known again for a long while, if ever. It is worth remembering, too, that every animal in this account eventually lost its position at the top of the water column, no matter how completely it once dominated the ocean around it. Anomalocaris gave way to the eurypterids and nautiloids. Dunkleosteus gave way to sharks and, eventually, to reptiles returning from land. The great sea dragons gave way to whales. Even megalodon, among the most capable predators this ocean has ever produced, disappeared roughly 3.5 million years ago, leaving behind an ocean that continued on without it, filling the space it left with other animals entirely. Dominance, across the full span of this account, has never once been permanent. It has only ever been temporary, however long temporary happened to last. There is something worth carrying from this into whatever comes after these words end. The ocean's oldest and strangest predators were never monsters in the way the word usually implies. They were simply very good, for their particular moment in time, at the one task every living thing on this planet shares, staying alive long enough to matter to whatever comes next. The water that built them is still out there, still dark in its deepest corners, still keeping whatever it keeps. For tonight, that is enough of an answer. The rest, as it has been for 4 billion years, can wait for morning.